We're going to learn some probability today. It's a side of math that gets a little wacky, and that might be why I like it. I also like it because, incidentally, it happens to be the engine behind my favorite daytime game show, Uncle Bob Needs a Date, in which we try to convince some or other member of the female persuasion to join Uncle Bob for dinner. So we're going to use this game show. We're going to see how the rules of this game rely on probability, and in the end, I hope we'll have some early ideas about the math. So, the game show. Uncle Bob needs a date, you're telling me. It will not surprise you to hear that getting Uncle Bob a date is not so easy. Usually a woman who hasn't already been committed to the state's charge has better options. So we'll have to see how the math makes it work. Here are the rules. The rules of the game. We start with 10 girls. Aren't they cute? The deal is these girls agree beforehand to go to dinner with whomever the game show assigns. Add 10 boys, 9 of whom are hunks. Hunks like Steve Buscemi and Pavarotti. So the whole game is made up of 10 lovely girls, 9 hunky boys, and Uncle Bob. That's the catch. The game works like this. Each girl picks at random out of a hat. In the hat are 9 white marbles, 1 black marble. Remember the chocolate war? The girls who draw a white marble get a date with one of the 9 hunky boys. But the girl who draws the black marble has to go out with Uncle Bob, which means he'll take her to Red Lobster because they have a 2-for-1 shrimp special, and he'll talk to her all night about things like quadratic zeros, and then he'll insist on going Dutch. Pony up, kiddo. This check ain't gonna handle itself. Now, you might be thinking, that's cool, I guess, but aren't we supposed to learn math? Well, the math is why the game works. In order to get to the math, we'll have to use our imagination for a second. Put yourself in the place of the girl drawing from the hat. Think of how different the game is under these two situations. Situation or scenario 1. You're still drawing marbles from a hat, but there's 1 winning marble and 1 losing marble. Situation scenario 2. There are 1,000 winning marbles and only 1 single losing marble. The game changes when I change those rules, doesn't it? And even if you can't put together a formal mathematical argument for why, I think you can just sense that the more ways there are to win, the better you feel about the game. All I've done is change the numbers of players. All I've done is change the probability, and here's the math. It had to come sometime, so it might as well come now. When we use the word, when we say probability, we will mean a certain relationship between 2 numbers, a relationship that's useful in studying random or random-ish events. So when I say probability, I mean the ratio of 2 separate but related ways to analyze a random event. It's the ratio of the count of the elements of a particular set of results you're studying in the random event, and the count of the elements in the set of all possible results of that random event. Since I just lost half of you, I'm going to say the same thing again in a different way. When we're talking about probability, we're presumably studying a random event, an action, an endeavor, whatever you want to call it. Something random is expected to happen. Usually, there are several possible ways this random event can go. If you flip a coin, it will land heads up or tails up. If you draw a straw from 3 cut to different lengths, your possibilities are the shortest straw, the longest, and the one in the middle. If you're picking a student at random in a class of 5, you have 5 students from which to choose. So much for that particular world, the world of all possible outcomes in a random event. But when we use the term probability, we need a little bit more information. We don't just need to know all the possible outcomes of an event. We need to know a specific set of outcomes, the count of the elements in a specific set of outcomes. If we're flipping a coin, we might be interested in when the coin comes up tails. Drawing straws, we might be interested in the middle straw. Picking from a class, we might be interested in just the girls. And now we can express probability for these events. We can express the probability of getting tails, the probability of the middle straw, the probability of picking a girl. So that's the concept, and now we can see if we can put it to work in the game show. Let's see if we can get Uncle Bob his date. If a girl is to pick at random 1 marble out of 10, the probability that she gets a specific marble is 1 over 10. One way to get a specific marble, 10 possible ways to select a marble in general. The probability that she gets any white marble at all is 9 out of 10. There are 9 white marbles in the box out of 10 total marbles. Change the rules a bit. Add 990 guys. If a girl is to pick at random 1 marble out of 1,000, the probability she gets that marble is 1 out of 1,000 total possibilities. If there's only one losing marble in 1,000, then her possibility or probability of losing is 0.001. Her probability of winning is a very encouraging 0.999, 999 over 1,000. And so maybe you start to see why I said probability was the engine of this game. It's this, when compared to that makes the game work. There's no reason, even in the 1,000-person game, that a particular girl can't lose. She can lose, but the abundance of ways to win gives her more confidence. Even enough confidence to risk an evening with Uncle Bob. But let's stick with this a moment and see what else we can learn about probability. Let's stay with the original rules. 9 white marbles, 1 black marble. Everyone picks a marble at random until the losing marble is chosen. So let's think about a few features of our original game. First, the white marbles for our purposes are all the same because the boys are all the same. They're all handsome, they're all charming, but they are, and frankly this is probably true in real life, more or less interchangeable. So if you get a white marble, you win. It doesn't matter which one. Related to that, once someone chooses the black marble, everyone else automatically wins. Because for our purposes, the only thing that really mattered was avoiding Uncle Bob. Okay, but here's one other feature. Things get more interesting as girls keep winning, because the girls don't put their marbles back. Say you're the 4th girl to pick. You have a new world. There are 7 marbles left. That's your new world, because 3 have already gone, taking 3 white marbles with them. So as you put your hand into the hat or the box or whatever, there are 7 marbles there, 6 of which are white, 1 of which is the losing marble. And that means your probability of winning has gone from 9 over 10 to 6 over 7. And I'm throwing numbers at you, but don't flip out. All I've done is remind myself of the definition of probability. Of course, we can keep playing the game to the point when 8 girls have picked, and none of them have taken the losing marble. Now 8 white marbles are gone. That leaves 1 black marble, 1 white marble, and 1 terrified young lady. She can almost hear Uncle Bob starting to rummage through his drawers for his gift cards. See how the math changes. The next person to pick, once 8 girls have gone, and all 8 have quote-unquote won, the next person to pick is going to have a 1 over 2 probability of winning. And naturally, a 1 over 2 probability of losing. Now, while what these numbers actually mean, and even what random actually means, is a fascinating and a challenging philosophical problem, the math part, the finding probability, the work with the actual numbers, should seem pretty easy so far. You should be able to get a number for probability by remembering the definition. If the probability of an event just is the count of the elements in a particular subset of outcomes over the count of the elements in the entire set of possible outcomes for the event, then the rest is just arithmetic. You can solve for a probability. Just set up your ratio and chug along. There is no reason, if you know this and this, that you can't get this. Now, of course, I say this to my students all the time, and they get seriously cheesed off because they're like, no, I just took a quiz or did a probability homework or whatever, and I literally wanted to stab myself in the face with a fork. OMG, Uncle Bob. They keep asking about poker hands, and I don't have a freaking clue. But you actually do. I'll show you what I mean. Take a traditionally tough question. What's the probability of selecting at random a full house in a game of 5-card stud? Doesn't seem like an easy question. But you know what? You'd be fine if I told you the number of ways one actually can get a full house. And if I also told you the number of ways you can get any of the possible hands in poker, then I think you've got the problem. You just apply the definition. It's when I withhold those numbers that the problem is no longer trivial. The actual work with probability isn't hard. You still just need to take a ratio of these two ideas. The tricky part is the counting. Since you don't feel like sitting down and counting out each possible poker hand one by one. There's a great, big, beautiful world out there. You have stuff to do. You have selfies to take. You have pictures of your dessert that haven't been posted on Instagram. You have a tweet war to start with Ariana Grande. That's the issue. You get the idea. I imagine you get the idea behind probability. You just don't have the time to count. So you'll need some sort of new math to help you, and that's our next step. Our next step is to learn how to answer some of the thornier problems of probability by developing our skills of counting. So we've been working for a while with Uncle Bob Needs a Date. It's a great game show, but in order to keep things fresh, I think we'll stick with game shows, but move on to something different. I think we should fire up my second favorite Emmy Award-winning daytime game show. This time not Uncle Bob Needs a Date, but rather Uncle Bob Needs a Lawyer, in which we assemble a revolutionary tribunal before which we can denounce friends and loved ones for counter-revolutionary activity and watch the hijinks that surely follow. This game will help us with counting because, as you might have guessed, there are a lot of ways for these dudes to cause mischief, so hold on to your burgundy. New game, new rules. So, it turns out I would like to form a revolutionary tribunal. And maybe I'd like to appoint some tyrants to some interesting governmental posts. Now, to do that, I need to choose from vetted, wholesome, reliably tyrannical folk who can send their own family to Siberia for no real reason and still sleep like a baby elephant. Or in the case of Robert Mugabe on his 90th birthday, eat a baby elephant. I couldn't make this stuff up if I tried. But the problem is, I have so many eligible dudes for the job. I only have a handful of posts, but I have so many tyrants. This becomes a counting issue. And here we're going to start to look at some of the math that really starts to trip people up when they're doing the probability problems. We're going to learn a lot along the way to answering some questions that arise from my background scenario. The first question is, say I have a pool of 40 eligible tyrants. How many ways can I arrange 40 tyrants among themselves? The second question, how many ways can I fill 3 revolutionary posts, Citizen-in-Chief, Secretary of Defense, and Secretary of the Interior Decorating, from a group of the 40 eligible tyrants? 3 posts from 40. Here's a third question. How many ways can I pick a panel of 3 judges from 40 tyrants? Now notice this is a separate, subtly different problem from the second, and one that will teach us separate and subtly different nuances in the mathematics of counting. Fine. Question 1. We're going to talk about lineups, arrangements, permutations. Let's start with some basic ideas about how to count the number of ways we can order a set of things. We want to build to 40, that's the question, and how many ways can we arrange 40 tyrants? But we might as well start with 1. Let's start with Fidelito, Uncle Fidel. How many ways can we arrange 1 tyrant? Well, obviously there's only one way to arrange Fidel. If he's alone in the universe, he's just there. There's no one to go in front of him or behind him. Well, that's fine, easy enough. How many ways can we arrange Fidel and Kimmy? I don't have a song for Uncle Kimmy. Frankly, I don't even know if they're allowed to have music there. But 2 tyrants, 2 arrangements. We can start with Fidel or we can start with Kimmy, and that's it. 2 possible arrangements. Now, when we move on to 3 tyrants, when we ask for the count of the number of ways that we can arrange 3 tyrants, it gets a little bit more interesting. We see the answer is this. We can start with any one of the 3, and then realize that there are 2 ways to arrange the 2 left over. Now, if you ask why are there 2 ways to arrange the 2, we'll just rewind like 10 seconds. But this move is kind of interesting. We say that we can arrange 3 tyrants by expressing the arrangement of 2 tyrants over 3 possibilities. That's a neat move. It's a neat move, and I can extend the logic indefinitely. Let's add a tyrant. Counting the number of ways to arrange 4 tyrants just means expressing over 4 possibilities the 6 ways one can arrange 3 tyrants. And if you want to know why there are 6 ways to arrange 3 tyrants, like I said, rewind about 10 seconds. Now, can you see how this is going to work out with 5 tyrants? Can you see how this is going to work out with 6 tyrants? Let's say I did want to count. I wanted to count the ways I can arrange 5 different tyrants. All I need to do is write out my 5 tyrants and realize that each one of these will be associated with the 24 ways one can arrange any remaining 4. The pattern is starting to get interesting. There's 1 way to count 1 tyrants, 2 ways, maybe 2 times 1 ways, to count 2 tyrants, 3 times 2 ways to count 3 tyrants, 4 times 3 times 2 ways to count 4 tyrants, 5 times 4 times 3 times 2 ways to count what? Something's going on here. We can start anywhere, can't we? We can start at any arbitrary value and make our count. This is an interesting and a powerful idea. It's actually so interesting and so powerful, we've developed a shorthand for it, the factorial, where any number followed by the exclamation point, the factorial sign, expresses the product of that number and every positive integer below it, all the way down to 1. So 4 factorial is 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times... You get the picture. So our answer for how to arrange 40 tyrants is actually 40 factorial. Now, I think this is kind of cool. I mean, imagine you want to arrange 100 people, tyrants, kittens, whatever. Say you're in detention and they've confiscated your Samsung. Say you're working for TSA and you're interested in possible ways 100 people can be crowded onto a 100-seat plane. Maybe you're doing a risk profile. Well, you have a couple of options. You can count out one by one that number ways there are to arrange 100 people, or you can work out 100 factorial to arrive at the same number. Now, even if you're doing things by hand, by the way, no calculators on the SAT as of spring of 2016, even if you're doing things by hand, the difference between working out 100 rounds of multiplication and counting all the way to this lovely number is the difference between a minor annoyance and a supremely bad day. Maybe this is why the TSA folk are always in a bad mood. I'm sure I'd make you take your shoes off too if you just made me count beyond the heat death of the universe. So this is an important principle, this idea of factorials, this discovery of the nature of counting arrangements. The factorial answers our first question, but it's only going to start to answer our next two questions. So our first question was, how many ways can you arrange 40 tyrants? And we know the answer to that now. 40 factorial. But I also asked something different. How many ways can we pick a Secretary of Offense, a Secretary of the Interior Decorating, and a Citizen-in-Chief from a pool of 40? So, to rephrase, how many ways can one pick 3 items from 40 and then arrange those 3 items into 3 separate and distinguishable places? Distinguishable is important. Well, to do this, let's build on what we already know. We already know that if we were interested in arranging all 40 tyrants, we'd start the analysis by realizing that the answer is gotten by taking the 40 candidates who can fill the first position and then applying all the possible arrangements for the next 39 to each of the 40. We know that. We also know that we can make the count for the remaining 39 with the same logic. We could do this all the way to the end, and we'd end up in familiar territory. But in our new situation, something very funny happens here. In terms 37 through 1. These circled terms, which we can also describe as 37 factorial, fall away in the new scenario because they're describing the number of ways I can arrange folk who are no longer part of the deal. I'm able to choose 40 tyrants for one post, no question about it. Once I've done that, I'm left with 39 for the next. Once I've chosen for that post, I'm left with 38 for the last. But the remaining 37 tyrants can't contribute to the count. In this factorial expression, they do. But in our new scenario, it doesn't matter how many ways one can arrange these tyrants because we don't have any room or need or care to arrange them. So arithmetically, we can express the new scenario as the ratio of 2 sequences of products, or as the ratio of 2 factorials. Now, this is where a formula that someone might have thrown at you during F period actually comes from, but I'd rather you learn the ideas instead of memorizing abstractions like this. If you learn the ideas, you can always build back to the abstraction again. So we've come to our answer, and we should move on to the last question, but before we end the video, I want to make sure we remember what we've done so far. We started with probability. We defined probability of a random event as a ratio between a subset of things we've chosen at random and the larger, or in certain cases equivalent set of things available for the possible choice. Then we realized that the tricky part of probability is actually counting the numerator and denominator, actually counting the elements that make up these sets. So we figured we might as well learn some counting principles, some clever counting principles. On our way to learning these clever counting principles, or one of these clever counting principles rather, is the factorial that we discovered. And we learned that it comes in handy if we want to count the many ways there are to arrange any arbitrary number of items, but it also comes in handy to do other things. For example, we took on a more complicated problem and realized that we could count the ways to arrange some number of things into a smaller number of available positions, so long as we're careful not to keep counting needlessly. That is, while there are 100 factorial ways to arrange 100 singers, there are much fewer ways to arrange those 100 singers into a ranking of a top 10. That's our progress so far. We got Uncle Bob a date. We switched around some tyrants. We filled 3 posts in our new revolutionary government with some of those tyrants. Now we turn to one last idea. What about our revolutionary tribunal? What if we just want to pick a 3-judge panel? Here things have changed again. Now, last time we picked positions, making Harry a citizen and Trotsky a or is this Trotsky? This is Lenin, right? Because Trotsky has a more angular face. So making Harry a citizen and Lenin a secretary was a different choice than making Harry a secretary and Lenin a citizen. Those would be counted as two separate choices. They were two separate posts. They had two separate names. They had two separate sets of responsibilities. Lord knows what they were. But they were different. Now, if you're assembling a panel of judges, things have changed, right? There's no real way to make distinctions like that. A judge panel of Idi, Harry, and Fidel is the same panel as one of Harry, Fidel, and Idi. In each case, they're just the three judges chosen. It's like picking finalists for a talent show. If you narrow down a field of 50 into 7 finalists, those 7 are, for the moment, indistinguishable. They are not ranked. They have no place relative to one another. Now, this means we have to tweak the math a bit. We need to add a step. We already showed what it takes to narrow 40 people into 3 slots, where having, say, Danton as citizen-in-chief was different from having him as Secretary of Defense. In our last question, the selection process meant that we had 40 choices for one post, 39 for a second, 38 for a third. But now we need to do one more thing. Since the math in our last question, would take into account not just the choice from the 40, but also the arrangement within these 3 slots, we have to account for that arrangement. We have to divide out that arrangement. Now, there are 6 ways to arrange 3 people into 3 spaces. We know this from earlier in the video. And this is going to come into play here. So we can now make a panel of judges by taking the math from our analysis from when position mattered and pulling out the one thing that is inappropriate for our current problem. The fact that the previous math, that this math in front of you, right now counts the 6 different arrangements of the 3 chosen tyrants as unique. Pull out the 6 ways, the 3 factorial ways to arrange your choice, and you arrive at your answer. The answer for how many ways you can form a tribunal of 3 judges from a pool of 40. We talked probability in general terms. By getting Uncle Bob a date, we realized that the tough probability questions tend to be tough precisely when it's hard to count the number of possibilities you're dealing with. So we played with tyrants, and we learned several different ways to count. We learned how to arrange things. We learned how to select a smaller group from a larger group of things, and then to arrange the selection in different ways. Then we learned how to select a smaller group from a larger group of things, but this time without arranging the selected smaller group of things among themselves. We learned a lot, but there's still a lot to do. Here's one obvious question. How does probability work when you're analyzing multiple random events? But that will have to wait for another time. For now, here's where you come in 2 ways. First, you need to practice. We ourselves want to make practice problems for you, but haven't decided yet if it's best to put out a whole slew of videos first and then make up the practice, or to put out the practice one by one with each video. We'd be interested in your thoughts on that, which brings me to the second point. We really want your input. What video do you want next? Should we continue digging deeper into statistics? Would you like to see an entirely new topic? Maybe an entirely new field? Are you interested in physics? How is the video looking to you? What about it works? What doesn't? What do you like? What would you like to see more of? Let us know. And until next time, I'm Uncle Bob, reminding you that school can be free and school can be fun.